Well, thank you, David, and good evening. As David said, we've actually been working for the last few years on some specific issues of climate change. We're actually semiconductor physicists, so we're not climate scientists. But in looking at climate change from our perspective, we've come up with what we've called an alternative analysis. An alternative analysis on the existing policy framework for and response to climate change. Now, this is actually part of a presentation that we've been invited to give at the UK's Department of Energy and Climate Change. We've selected some portions from it. And I think I should say before I start, we sort of feel it's fairly radical and in many ways could be controversial, and we think maybe even provocative. So we're sort of hoping that you do find it interesting. I'm going to go through the presentation. My colleague Evan Parker is then going to chair a debate. So you can throw all the sort of used vegetables and fruit at Evan when he comes up and does his part of the discussion. So, an alternative analysis. What am I going to talk about? Well, first of all, just very briefly and very quickly, a review of the science, and it will be brief, but what we think we're able to bring to it, and we hope we're able to bring to it, is a different perspective of what the science is actually saying. And from that, we're going to say what the existing policy is. So that, in many ways, section 1 is a historic perspective of where we're at. Section 2 is then all about communication. And we'll talk a little bit about the communication of the existing science and how that has been presented. Basically because we think that's been flawed. But again, we'll go through that and we'll propose an alternative communication scenario. And then finally, we'll present our alternative strategy. Now, as I mentioned at the beginning, we're actually not climate scientists. So I just want to give very briefly a perspective of why we're interested in this field, what brought us to our attention. Now, if you're a semiconductor physicist like we are, you tend to have this rose-tinted perspective of semiconductors. They're wonderful things and they can solve many problems. So we came to it with preconceived ideas and we addressed specific issues by those. And I'll just go through those very quickly. The first one, and I'm definitely using the royal we here because this was all pioneered by my colleague Evan Parker, that on Warwick Science Park we have a spin-out business, 25 people, dedicated to producing a new energy generation system. This new system is based on a technology called concentrated photovoltaics, and you may be aware of it or not aware of it. Photovoltaics, I think, is very well known. Concentrated photovoltaics is one step advanced on that, in that it employs basically a means of concentrating the radiation onto a photovoltaic cell. Now, where the semiconductors come in is basically in the photovoltaic cell. And what we've been able to do, and what the semiconductor scientists around the world have been able to do, is produce extremely efficient photovoltaic cells, which makes the whole process much more efficient. The problem with those is they're very sophisticated, they use sophisticated materials, take long times to fabricate, and so they're expensive. So in order to get around the issue of the expense, if you have one photovoltaic cell per large surface area, you can optimize the cost efficiency of the whole process. It doesn't become the cost determinant in the photovoltaic cell, so in the whole system. So what we have designed here is a holistic design in which we've integrated a lens system with a solar cell to get maximum efficiency, and most importantly, the real driving force, cost competitive with fossil fuel. The objective of this is to beat oil, beat the price of oil. There's a roadmap by 2015 whereby we can achieve that. Second area, somewhat more blue sky. In fact, completely blue sky. It's conceptual. But what happens if the temperatures do run away? If we get runaway temperatures, what can we do? Well, this is a geoengineering concept, and it's based on actually relatively well-established silicon processing technology. So there's a little bit of silicon, We call it a dream particle. You can see it's quite small, so it's basically a piece of dust, silicon dust. You use just conventional silicon processing. It has inbuilt in it intelligence. It has a receiver and transmitter, so it can be controlled from the Earth locally. It has its own engine system, microelectronics mechanical system, so it's got an inbuilt motor, and it's got an energy source, the photovoltaic cell, where it gets the energy from. One surface has got a mirror finish. Just send it up in the atmosphere. It's self-driven, so self-powered. Control it from Earth, and it can reflect radiation, a percentage of the radiation. When you want to switch it off, you just flip it round, and it switches off. Not quite as straightforward as I've made it sound there, but a little bit challenging. But so that's how we came into this field. That's just to give you a perspective. And like everyone else, we have our own biases and perspectives. So back to the science of climate change. I don't think I'm going to say much more than this, really. It's really complicated. I'm sure you're very aware of it. I mean, it's based on a very complex four-dimensional analysis of all the input parameters, which vary from the radiation in the cloud system, hydration system, the fluid mechanics within the whole of that, the impact of the oceans, the land mass, the carbon cycle, and specifically the clouds. A very complex procedure. It's dynamic, so you need it to be four-dimensional. It really is sophisticated maths and physics. One of the big problems, one of the big challenges, is a key factor is turbulence within the atmosphere, particularly interfacial turbulence. Now, many people who've been involved in turbulence know this is a bit of a challenge, and every physicist always has to quote our guru whenever we go into a new subject area. And what did Einstein think of turbulence? Well, he thought somebody could explain quantum physics to it, but he really needed divine intervention to understand turbulence. So it's a big challenge. It is, we shouldn't underestimate this. This is a really big, complex subject. There's an additional problem. The additional problem is if we then look at our input on the climate, we bring a whole other range of new complexities into it. If you take the first level, at the first level, CO2 and the greenhouse gas effect is well understood. It's well modelled, we appreciate it. We could define that and predict the impact of CO2 pretty accurately, maybe very accurately. There's still some slight debate on that, but maybe very accurately. The problem is, it's in a climate. It's not a laboratory experiment where we change the CO2 levels. What happens is any change in the temperature impacts a whole range of other parameters. And those other parameters then have positive and negative feedback cycles. Now, I won't go through all of these, but some of them we know and they're reasonably well modelled. Others are less well understood, but are still included in the model, so the best we can. Some big ones, oceans and I would say clouds as well, are at a very early stage in their development. There's also this lurking fear of some very scary things called the tipping points, irreversible reactions, which we really are at a very primitive stage, but people have done some speculations of those. Those are actually the biggest concern in runaway temperature effects. They're not included in any of the models, but they're there and people are aware of them and people are trying to understand them. So it's an extremely complex process, and the addition of our input is extremely complex as well. The first thing to say is that there isn't a conspiracy to mislead. The climate scientists working in this area are working transparently. They're some of the best laboratories and some of the most prestigious scientists in the world are focused on these areas. So they would admit absolutely readily that the models and our understanding of the physics is limited and incomplete. They're quite limited and incomplete, and that an accurate climate prediction is not presently within our grasp. And one couldn't say with any great confidence that it's going to come in the near future. People working in this area have access to very sophisticated computers. And they say, with some validity, that have more powerful computers, they could make the models more accurate. That's true if the actual understanding of the physics was actually greater. And that's with a big step, and it's always tough to predict when we would actually overcome that. So that's the first thing, that the climate scientists are saying, yeah, it's a tough area. Now what we have here is and the next couple of slides, is our interpretation of what we believe the science is saying. To our knowledge, this is a new representation of it. It's a graphical representation which we think will give some insight into not only the science, but in the way to progress in this scientific basis. Now what we've drawn here, and those are the blue curves, are a set of probability profiles. So if you have probability on the y-axis and temperature on the x-axis, for a specific level of carbon dioxide in the atmosphere, and the first objective is to get the carbon dioxide level, the first target is 450 parts per million, you have a probability profile of what temperatures will occur at that concentration of CO2. So we can't predict it accurately, so we get a probability profile. But there's a few things to notice on that. First of all, it's quite a broad profile on our most well understood area of CO2 concentrations. And depending on the robustness or the sensitivity of the climate to these CO2 levels, it can vary within 5 to 10% chance it's 1 degree, 5 to 10% it could be 3 degrees. So quite a big error out of 2 degrees centigrade. Some interesting thing as well, it doesn't approach zero very rapidly. Some of the latest predictions are that it could achieve 11 degrees and still be approaching a small percentage chance of being 11 degrees. So this is a very broad profile. The additional complication is as you increase the CO2 level, you get increasing uncertainty. Because the other factors, the feedback factors, which are less well understood, become much more dominant in the whole process. And maybe some of the tipping factors also become affected by it. So what you have is a much broader profile for high levels of CO2. So that really illustrates essentially what a lot of the science has been working at, is understanding what temperatures the Earth's climate would achieve. And this is increase in temperature over pre-industrial levels with certain levels of CO2. The first thing we'd say on that is actually it isn't temperatures that matter, not directly. What really matters is the impact of the temperatures. You know, if a few degrees centigrade was quite benign, was quite positive, then it wouldn't be a big issue. If 10 degrees was a positive increase in temperatures, there wouldn't be a big issue. But in reality, there is a big issue, and the reality is that the impact of those temperatures on the environment and humanity can be seen to be very significant. Now, what we've drawn here is basically an illustration that all that does is adds to the complexity of the situation, because what we're saying is that we now know that there's a great deal of uncertainty in the temperature. But what we also know is that the impact on the environment is a highly complex situation and very tough to actually accurately define, certainly in sort of local geographical terms, just what that impact will be. There's some assessments and some analysis, but that itself has uncertainty. And these uncertainties are cumulative. So the uncertainty in the natural climate is an additional factor to the input we put in, the anthropogenic impact. The impact on the environment then has an uncertainty itself associated with it. And finally, the impact on humanity is really multifaceted, because it depends on how we respond to it, how we react to it, what's put in place, particularly what adaptation processes are put in place. So it's really complex. And the question then is, what do you do about having this whole range of different complex scenarios and inputs? Well, let's look at the impact on humanity and see what that tells us. Well, this refers back to the original probability profile curves. And what we've put on that is this terminology for what is believed to be the impact. Now, it's just terminology, it's just words, and people have tried to put economic factors and try to be more definitive in that, but I think they sort of say essentially what they mean to imply, that it goes from the benign to the catastrophic. But the width of those is illustrative of the error in just what temperature those impacts will occur at. So you can see a very wide range of temperatures could be catastrophic, very wide range severe, wide range benign, and at certain temperatures you overlap all three of these areas. So you can't specifically say at a certain temperature a particular scenario will occur. I think what you would say definitively that the risks are too high for inaction. You can't use the uncertainty as an excuse for inaction that some people have said. The minute you have risks like that, the potential impact like that, then it's clearly a very serious potential problem. It's just what can you do about it? How can you address that? Well, let's have a look what the existing approach, the existing policy of addressing those issues are. Well, as I said, the key issue is the policy driver is what's the impact on humanity. And the approach universally taken, the global approach, is essentially a mitigation policy which is focused on CO2 emission reduction targets. That's the cornerstone policy. There is also an adaptation policy, it's just less visible. It's less visible, it's less presented, it's protected, but there is an adaptation policy. But the world is relying upon a CO2 emissions reduction targets actually addressing these issues, addressing the problems that we have in this area. And that's the cornerstone one. And one would say, well, why not? Because that appears to be the problem, and there appears to be a potential catastrophic results to it all. So what's wrong with that approach? Well, unfortunately, there's a few things wrong with it. And it's a bit tough for that young gentleman there. Because at the moment, all we can say is there is very limited buy-in to that policy. It's also very variable. You only have to look at the political situation in America to see how it fluctuates, political situation all over the world, how it will fluctuate. And public opinion is mixed on this. People do different measures on it. But considering the scale of the problem, the fact there's limited buy-in is a big issue. The other one is we can't say with any great confidence that we will actually achieve the emission reduction targets that we're being set. The history to date is that we probably won't. So here we are relying on a system with a limited buy-in, and we may not even beat the targets that we want to achieve. And finally, as I said, as far as the uncertainty profiles go, it could all be too little, too late. So big issue, big problem. And why are we in this situation? Why are we facing this potential global problem of this scale and not actually having a policy in place that's addressing the issues successfully? Well, we think there's a fundamental reason for that. And the fundamental reason's very straightforward, and interestingly, it encompasses many areas of science, in that the uncertainty in the science and the scenarios have not been clearly accepted or effectively communicated. The problem was, and it's a problem that often happens when complex issues are then presented and the establishment communicates those on, there is an intolerance to ambiguity, an intolerance to the uncertainty of saying that. People just don't like, because people think, well, that's going to lead to inactivity and no action on it. And it happens in many areas, but in this field it's a big issue. So what do we do about that? Well, the problem is, because this uncertainty has not been projected, we get a number of consequences. You get the Great Divide. The goodies and the baddies. Well, I'll let you decide which side is which, but it's clear now there are almost two completely polarised encampments. One of the problems when you get that sort of polarisation is that open debate and constructive analysis of the situation is extremely difficult. These have become dogmatic beliefs more than the scientific analysis of it. And quite frequently you get, because we all do it, if we all think something is the correct thing, we look for any data that supports it, we grab onto it quickly and present that as a justification for why we're doing things. And there's been many examples by both sides of false predictions being made. And if anything undermines a case, Himalayan glaciers melting or whatever, then it's making a false prediction on the case. I think there's a more serious issue than that. And I apologise that this is somewhat UK-based, but I've tried to use a cross-section of the political classes in the political opinion in the UK and also social opinion, in that actually questioning global warming in any form has been damned as heretical. It's not the thing to do. Just look at the terminology used. Now, I'm sure this is not unique to the UK. Well, it isn't unique to the UK. Declare war on climate sceptics. True climate sceptics must stop the war on science. The views of climate sceptics are extraordinary. That, I think, is a fundamentally flawed communication strategy, particularly the criticism of scepticism and sceptics. Physics is often referred to as organised scepticism. And I'm sure you know areas of philosophy are based on scepticism, fundamental to it, enlightenment. It seems such a flawed approach to view scepticism, questioning anything, as fundamentally wrong. Now the problem is, and the people would say this, is that people who are so-called climate deniers masquerade themselves as skeptics. That I don't think excuses the people who believe in the science and believe in that actually also saying that skeptical approach is wrong, because it's perfectly reasonable and quite valid, considering the range of scenarios that occur, to question the science and question particularly some of the outcomes and the predictions on it. So how do you change that? What do you do about that? Well, before you do, this is really just an illustration, I think, of what's happened. Because if you're a neutral, if you're an agnostic in this debate, if you don't really get fully engaged by it, and you ask some questions, and somebody damns you as being heretical, or even immediately dismisses whatever you say, because it can't be right, then I think you would naturally fall into the skeptics' plant and have more sympathy for what skeptics are saying. And the problem is, I think, that the public opinion and many people's opinion has slipped down towards that skeptics and deniers area. And that's made it very tough. And it's almost made the whole thing very separate, and it hasn't allowed a completely open and constructive debate about it. So what do you do about it? Well, you do the obvious thing, easy to say, but not that easy to do. I have to say, you accept and present the uncertainty. You change the message. Now, one of the reasons people say that you don't do that is that it'll stop inaction, that it'll just complicate the issue, people won't understand it. Actually, I think that's unreasonable, somewhat demeaning to say, a sort of patronising approach. Everybody deals with uncertainty in all the major issues of their life all the time. There's a whole industry, insurance industry, based on it. I think people would fully understand and appreciate being spoken to as just saying what the science really says. It may not be an easy message, but I think it's worth saying that. I think more interestingly, very interesting, is the skeptics would be embraced by the analysis. True skeptics would be embraced by the analysis. You wouldn't have a terminology problem. Reasonable to question the whole thing. So they would be part of the overall perspective of what it's saying, what the science is saying. And I think the deniers would be completely isolated. What are they denying? Are they denying that CO2 is a greenhouse gas and that it'll have an effect on the climate? And so the whole debate will change, and that seesaw would change, and the middle ground, the agnostics and neutrals, I think would quite strongly move towards the believers' side and the believers in the science side. So I think you'd get much more public positivity about whatever one wants to do. Let's say you've done that. Let's say we've presented the uncertainty. Does that have any impact on the strategy, the approach? Okay, so we've got now everybody on our side. They know what we want to do. Do you have a different strategic approach because of that? I think you do. And you have a strategic approach, and again, people may say they're doing this, but I think it's actually then very clear what you do. The uncertainty needs to drive the agenda, and the strategy would be based on risk management. You'd look at the risks and then decide what policies to introduce. You know, how do you best get that boat to land without everybody tipping out of it? So risk management is the obvious development on the strategic, on the uncertainty. You'd look at the strategies. Now, just what are those risks? Now, going back to a previous slide and slightly added a couple of dimensions. On the classic definition of risks, it's impact versus probability of that happening. And as I mentioned, the impact goes from the benign to the catastrophic, and then you have uncertainties in the temperature profiles. What I've done in this area is split the impact up and split the graph up into 3 sections. The reason I've done that is I think that makes you then evaluate all the possible scenarios. Just look at this scenario. In Zone A, it could be that whatever we do to limit CO2 levels, that we finished up in Zone High a relatively benign temperature increase, almost irrespective of how rapidly and quickly we responded to it. So one has to be very careful about the policies you introduce, that they're not productive, efficient, and don't damage the life expectancy or reduce the life enhancement that energy definitively does. If you look at the other section, you have the potential, even for low levels of CO2, of extremely high temperatures. So you have to have a policy which encompasses both the fact it could be benign and both the fact it could be runaway high temperatures and catastrophic impact. So how do you do that? How do you cover that whole range of different possibilities? Well, it's not simple, and it has to be multifaceted. You have to have both an adaptation and a mitigation policy. So both policies have to be there. There are very good reasons, strong arguments to say the immediate priority and the immediate objective is to look at what adaptation is necessary, assuming the high probability there will be a certain temperature increase. I've heard it variously quoted, assume a 3-degree centigrade increase by the end of the century and put an adaptation policy in place based on that. Now, fortunately, we have a very good model of how to do that, and that's in Holland. They've been doing this since the 50s, institutionalised adaptation. They adapt their environment depending on the changes in the climate and the conditions around them on a regular basis. And they use the words institutionalised because it's continuous. It isn't an immediate thing. You do it all the time. Whenever you're planning anything, when you're putting new services, new housing in there, a new metropolis, power systems, they also take into account what the temperature changes could be and what the climatic changes could be. That makes sense for Zone A. For Zone C and the mitigation policy, it seems completely inappropriate not to have some form of geoengineering, just in case. Just in case temperatures occur here. One would hope one wouldn't have to use it. But if there is runaway temperatures, not having developed a geoengineering solution would leave us completely in a vulnerable position. But what I'm going to focus on, most of that probably sounds obvious. The more challenging is a mitigation policy. How do you introduce a mitigation policy which encompasses the fact that limited temperatures could occur or very significant temperatures could occur? How do you do that? Given the fact that cheap energy is particularly life enhancing, if you make energy more expensive, then there will be repercussions to it. So you've got to be very careful about the policy you introduce in that end, just in case, even if you did nothing, the temperatures will still remain relatively benign. To the same extent, it's got to address the fundamental issue, because you never know, we could finish up there. Well, let's have a look at the existing policy. And this may be the first one of a few controversial things we say. The existing policy is based on CO2 emission reduction targets. Now, I'm sure many of you work in environments that are target-driven. I've spent many years in a US corporation in which it was absolutely target-driven. The important thing about targets, as people know, it's a very subtle thing to introduce into any operational system, is that people need to actually be engaged and bought into the targets and appreciate that they have some contribution and they can achieve the targets. There has to be very sort of positive feedback that we know we can achieve those targets. If you don't have those in place, if you feel that something's happening outside your control, which is impacting it, it's very difficult to get the buy-in and also the positive results. And you can easily get injudicious actions occurring. I'm sure, as you well know, if you're in a business environment and say to a general manager, quickly make more profitability, get rid of the R&D department. Say to a sales and marketing, we need more sales, then you'll almost certainly get sales that you don't want. There has to be a subtlety and constraints about what you do. Otherwise, you get injudicious actions. You get the wrong things being done. And I think there are some good examples on that. Now, we'll come back to this one a little bit later. But I think more importantly, it can divert you from the real issue. What is the real issue? Yes, we want to reduce CO2 targets, but what do we have to address to do that? Well, obvious statement, but needs to be said, it's really all about energy. That's what it's about. If a clean energy system existed that was proven and cheaper or comparable to than hydrocarbon-based systems, then we may not have the solution immediately because you need to deploy it and institute it, but you could see a route to achieve it. Maybe an obvious thing to say, but it needs to be said. That needs to be the key area, the area that is looked at and positively addressed. I would say the first thing is change the focus. Change the focus to developing properly audited, clean, sustainable and deployable clean energy systems. And the key in there, make these cost competitive. Cost competitive in a real sense, not artificially masked by some government funding program or some artificial program of doing it. Real cost competitive energy systems, often referred to as levelized equivalent costing. So it's not masked by the artificiality of national inputs or grants or other things. The thing about that is it would be extremely positive. It was something that people could latch on to. It would be wealth generating. And what needs to be done, and what our proposals for the UK government and what we think internationally, is that there should be a programme to develop that. Maybe a Manhattan-style programme, or a programme involving scientists around the world to allow them to be innovative and to allow them to come up with these solutions to address these problems. It's a big challenge. We come from an industry that typically spends between 15 to 20% of its revenues on R&D. It's because it's an innovation-led industry. We need that level of innovation in this type of industry to really try and address and try and come up with the new way forward. So fundamentally, what we're proposing is move away from the CO2 target mindset. Right, we want to reduce CO2, but don't necessarily make it the universal, visible target that everyone needs to go to. Make it a clean global energy system. And it needs to be global. Here's another important and maybe controversial thing. Don't be lost by any parochial perspective of it being a domestic issue. So don't confuse it by energy security. Okay, energy security might be nice, but that isn't the same as addressing the CO2 issue and the global energy problem. Don't confuse it by energy efficiency, because that's a different issue. The world needs energy, there's an increasing need for energy, we've got to provide it by clean sources. So make it global and make sure somebody can make money for it, the environment, the conditions and the vehicles that we know are successful for get people to make money, allow people to make money from the green dollar. So what are the big messages that we're projecting? They're essentially, the first three are largely either historic or really addressing the establishment and the message that's being portrayed. First of all, we must communicate and accept the uncertainties in the science. Very interesting. This seems not just this field, in many other fields this is an issue. And the consequential impacts on the environment and humanity. So accept the uncertainties, embrace them in the strategic response, and drop the CO2 emissions reduction target culture. Thirdly, adaptation and mitigation should be no regrets policies and should include geoengineering. And finally, effective mitigation is all about low cost, clean, sustainable energy. Make this the cornerstone of the visible policy, not the CO2 emissions. Well, that concludes the presentation. I'd like to hand over now to my esteemed colleague. By esteemed, I mean quite old. Colleague who's going to actually now lead the debate and talk to you about the debate areas that we'd like to discuss with you.
Okay, moving on now to the what I think is the real fun part of the evening. If I can press this on. Debate is all about the new energy landscape, and I guess this involves you to a great extent. The title, All Hot Air and Wind. This is, the backdrop is a picture taken this year from China. It's got 100 wagons full of coal on the back of that engine. That currently powers 70% of China. That's set to treble by 1930. Topics. I believe you're in 4 groups, and what we'd like to do is to assign one of these topics to each group, and then for you to you can go away to your little rooms, or you can stay here and talk about how you're going to address these questions. The first one is, should we abandon CO2 emission reduction targets? As David has spoken of, he's suggested that this should be done. A huge step for sure, and we'd like your thoughts on that. If we could arrange that you appoint a sort of spokesman from your group who will speak when you return in about 20 minutes, who will speak to this question. So group number 1, the spokesman will speak and give a sort of cumulative response for what your group thinks about that, whether it's complete nonsense or whether we should be thinking about that. And then after he's spoken, then it's thrown open to everyone in the room to input on the subject. Group 2 is a focus on energy security adversely affecting sustainable energy policies. If Group 2 could think about that, and this is certainly a concern that we have, that this obsession or very strong focus on energy security is influence how governments are pushing, encouraging the people in the industry to work. The third one, which I believe some of you are already on, can CCS, carbon capture and storage, and nuclear really deliver the medium-term solution? And that's until we reach the halcyon days where all our energy is produced renewably, sustainably, with no CO2 associated with it. Can those 2 technologies deliver in the meantime? And we're looking sort of to the end of this century, maybe 2075, before that could ever take place. To establish a new energy generation process is going to take many decades to come into force for sure. And then the third question, and this really doesn't relate to the fact that we do have a solar energy company. I can assure you we're very interested in your views on this. Do you think the only sensible long-term global energy supply system that we should use to generate this renewable energy is solar? If the Group 4 could address that question. So the spokesman coming back with initial response and then open to the rest of the people. So it's all over to you. On just the backdrop of this, you'll notice this is the CO2. Can't see it very clearly. This is CO2 measured as a seasonal variation in CO2 levels due to the greenery that comes up. And as you can see, since 1960, it's gone up pretty uniformly up to 2010, when we're at about 390 parts per million of carbon dioxide. So I now leave it over to you, and I'll see you in 15 to 20 minutes' time. We're due to finish about 7:30.